Okay, so here's the problem. We were given a map, the general formula, and then and two bases, and then we found the matrix G by finding the basis action of the three basis vectors. So here's the three columns, and they immediately form the matrix. And then in order to find the rank of the map, we put the matrix that represents the map into echelon form and find the rank of the matrix, which is the rank of the map, which turns out to be the same as the dimension of the codomain space R2, so that means that G is onto. Now, from the dimension formula, we know that the rank plus the nullity equals the dimension of the domain, which is 3. So the rank 2 plus the nullity equals 3. The nullity is 1, which means that G is not 1 to 1. Okay? Now, if we wanted to find the range space and the null space, we could go back to the general formula, or we could go, let's say that we can find, what we want to do is we want to find 1, 1, 1, 1, 0, 1. This represents the map via multiplication from vectors in V, the domain, to the codomain. So if we choose here 0, 0, all the vectors here are in the null space. So solve this equation, it's a matrix equation for a linear system. Solve this equation for null space. Okay? So, well, how would we do that? Well, we would just say 1, 1, 1, 1, 0, 1, 0, 0, right? The augmented matrix for the coefficients A, B, and C. Oh, not A, B, and C, X, Y, and because I've already said X, Y, and Z. X, Y, and Z. So we would do minus row 1 plus row 2. And give 1, 1, 1, 0. 0, minus 1, 0, 0. So therefore, minus y equals 0. And y equals 0. And the first equation would be x plus y is 0 plus z equals 0. So x equals minus z. So therefore, the null space equals all the x, y, z's here that solve the system. Well, that's all the vectors of the form y is 0 and x is minus z, where the free variable z is any member of R. So we can then write this as z times minus 1, 0, 1, such that z is a member of R. And clearly, this is a one-dimensional space, so the dimension of n equals 1, because this is the basis vector. So the basis for n is just minus 1, 0, 1. So we've actually constructed a basis for the null space, and you see that its dimension is 1, so the nullity is 1. Okay, now what about the range space? Well, the range space is 1, 1, 1, 1, 0, 1. I put in any vector here, and I get out u v over here, right? This is the x, y, z, or any is for any vector here. So what I want is all the vectors u v, right? Because so the range space equals all the UVs such that this is true, right? So I want to solve this. I want to solve this in some sense. What I want to do is I want to find. I want to find the u and the v in terms of X, Y, and Z, right? Now, if we look at, maybe make this sort of see what this is going, what this is coming from. Where is? Oh yeah, here's the. So here's the range space, X plus Y and Y. This is, we know this is the range space here, right? And so, because it's this is the null space. Where's the range space? Here's the range space. Oh, this was a different example. Okay, so here we want to find, so here the range space is all of these things, X plus Y plus Z, X plus Z, right? So that's what this is saying is we want to find, what we do is we multiply this out, right? If we multiply this out, we get 111 times X, we get X plus Y plus Z, and X plus 0, Y plus Z, X plus Z equals the U and the V. And so we want the U and the V for all of these things. So basically we say the range space equals X plus Y plus Z, X plus Z for X, Y, and Z members of R, right? And that's going to equal X times 1, 1, plus Y times 1, 0, plus Z times 1, 1, X plus Y plus Z members of R. And you can see right away that this vector and this vector are the same vector, so that we could appeal to the theorem. This is dependent vectors. This is going to equal X times 1, 1 plus Y times 1, 0, such that X and Y are members of R. And if you didn't like just throwing this out, what we could do is we could say, we want to find a linearly independent set of these vectors. So we'd form the matrix 1, 1, 1, 0, 1, 1, and so we want the column space here is the range. These vectors span the range space, the column vectors here. So we want to find a linearly independent set. So we take the transpose of this. First column is first row, second column is second row, third column is third row. Then we would say minus row 1 plus row 3 would give 1, 1, 1, 0, 0, 0, right? And then we would do minus row 1 plus row 2 to give 1, 1, 0, minus 1, 0, 0. And then this would be an echelon form. So therefore this is going to be a basis for this row space here. But then we take the transpose back. First row is first column, second row is second column, and we take the non-zero rows. So therefore we have that the basis equals 1, 1, 0, minus 1. So that's another basis. And again, here you can see this is a different basis. And I could manufacture, I can get this basis from this one. They're both bases, okay? So this one here, by deleting one of these, isn't necessarily the same one that you get here, but this is a mechanical way, and this appeals to the theorem that these vectors are linearly dependent. But there's two ways to find the range space. So we can say here that the range space equals, say, R times 1, 1 plus S times 0, minus 1 for R and S members of R. And those are two different bases for the same space, but still a representation of the same space. And you can see that the dimension of R equals 2, so that equals the rank of the map, rank of map, and that shows you and since the range space is two-dimensional, that means this is isomorphic to R2C, which is the codomain. So the range space is the codomain, because spaces that have the same dimension are isomorphic, essentially the same. Stephen, you look puzzled.
What is it?
An isomorphism says there's a one-to-one onto map between two spaces. So, because this is two-dimensional, like I may not recognize this as a basis for R2C, but this range space, unfortunately, I'm using the same notate. The problem is, okay.
I was confused because I thought we were talking about G, the map G being isomorphic.
Oh, no, map could be an isomorphism,
Right.
but it's not isomorphic. Now, G is not so G here is not an isomorphism. Because, in fact, no non-square matrix can be an isomorphism.
Right.
So here, since this G is a 2x3 matrix, and you can see right away it's not going to be one-to-one.